This video is about Earth in space. This is an artist's concept of the solar system, showing the planet's orbits. Earth is the third planet from the Sun. The relative sizes and distances of the planets are also depicted. Additionally, it shows the solar system viewed toward Earth from the Moon. Earth has numerous motions as it travels through space. There are 7 notable motions, with 3 being more apparent on the surface. Earth follows a gigantic helix path, moving incredibly fast as it accompanies the Sun and the galaxy through space. Eratosthenes estimated Earth's circumference. He observed that the Sun's rays were vertical at Syene, but made an angle of a little over 7 degrees at Alexandria at noon on the same day. He attributed this difference to Earth's curvature. As 7 degrees is about 1/50th of 360 degrees, Earth's circumference had to be 50 times the distance between the two towns. This diagram illustrates the principle used by Eratosthenes to calculate the Earth's circumference based on the difference in the Sun's angle at noon in Syene and Alexandria. This image shows Earth as seen from space. Now let's explore the shape and size of the Earth. The solar system is a disc-shaped nebula with a turning, swirling motion and includes the plane of the ecliptic. Ancient Greeks believed the Earth was round because a sphere was considered a perfect shape. They also observed Earth's circular shadow during a lunar eclipse and watched ships disappear over the horizon. The Earth is not a perfect sphere. It's an oblate spheroid, flattened at the poles and having an equatorial bulge. The North Pole is slightly higher, and the South Pole is slightly lower than the average surface. The equator has a bulge, and there are depressions in the Pacific and Indian Oceans. Earth's shape is slightly lopsided and pear-shaped, but generally it's considered an oblate spheroid, which deviates from a perfect sphere as shown in this diagram. Next, we will discuss the motions of the Earth. This diagram illustrates the Sun's position on the celestial sphere at the solstices and the equinoxes. The Earth has 3 main motions independent of the Sun and galaxy's motion. It has a yearly rotation around the Sun, rotates on its axis approximately every 24 hours, and its axis slowly wobbles as it revolves. Foucault's pendulum demonstrated that the Earth turns. Since no external forces change the pendulum's plane of swing, its apparent change of rotation is due to us moving with the rotating Earth. The Foucault pendulum maintains its swing plane, while the Earth rotates beneath it. The degree of observed turning is dependent on the pendulum's latitude. Revolution is the Earth's orbit, which is slightly elliptical and takes about 1 year to complete. The orbit forms the plane of the ecliptic. The Earth's average distance from the Sun is 150 million kilometers, and it moves fastest at perihelion in January and slowest at aphelion in July. Solstices mark the extreme points of the Sun's altitude. The summer solstice occurs around June 22nd, when the noon sun is at its highest altitude. The winter solstice occurs around December 22nd, when the noon sun has its lowest altitude. The seasons are caused by the consistent tilt and orientation of Earth's axis as it orbits the Sun. The North Pole points toward the Sun during the summer solstice and away during the winter solstice. An equinox occurs when the Sun is halfway between the solstices. At this time, Earth's axis is perpendicular to the line between the Sun and Earth's centers, and daylight and night are of equal length. The spring equinox is on March 21st, and the autumnal equinox is on September 23rd. The length of daylight is determined by the relationship between Earth's shadow and the axis tilt. At the equinoxes, day and night are equal. During the summer solstice, the North Pole is in constant daylight, and during the winter solstice, it is in constant night. We know the Earth rotates because other planets rotate. A pendulum's plane of swing changes, and the motion of objects above Earth's surface can be observed. Rotation causes the Coriolis effect, deflecting moving objects right in the northern hemisphere and left in the southern hemisphere. Earth's rotational velocity is greater at the equator and decreases towards the poles. This variation causes the Coriolis effect, an apparent deflection of moving objects to the right in the northern hemisphere and to the left in the southern hemisphere. Precession is the slow wobble of the Earth on its axis. This motion causes the Earth to swing in a slow circle, similar to a spinning top. Precession is similar to a spinning top wobbling. The axis of the top traces out a small circle, demonstrating the motion involved in the Earth's precession. The continuous, slow precession of Earth's axis causes the North Pole to trace a small circle over approximately 26,000 years. Next, we will discuss the concepts of place and time. To identify a place, the Earth's axis sets the north-south reference. East-west parallel circles are called parallels, and the distance from the equator is latitude. North-south running arcs are meridians. The prime meridian runs through Greenwich, England, and distance east or west is longitude. Identifying location on a sphere is challenging as there are no natural reference points like edges on a flat surface. Parallels, which are circles parallel to the equator, are used to define a position north or south. This illustration shows some of these parallels. If observed from Earth's center, latitudes range from 0 degrees at the equator to 90 degrees at the North Pole or 90 degrees south at the South Pole. Meridians run from pole to pole, perpendicular to the parallels. They provide a reference for specifying east and west direction. If you could see inside the Earth, you would measure 360 degrees around the equator and 180 degrees of longitude both east and west of the prime meridian. Some parallels are important for understanding climate changes. These include the Tropic of Cancer at 23.5 degrees north and the Tropic of Capricorn at 23.5 degrees south, marking the limits of the Earth's tilt toward the sun. At the summer solstice, the noon sun is directly overhead at the Tropic of Cancer. 24 hours of daylight occur north of the Arctic Circle. The winter solstice is the reverse, with the sun over the Tropic of Capricorn. Let's look at measuring time. A sidereal day is 23 hours, 56 minutes, and 4 seconds, based on a star's crossing of the celestial meridian. In contrast, a mean solar day is 24 hours long. A sundial indicates the apparent local solar time, which is based on an average solar time and is usually different from clock time. Yearly time is the time for Earth's complete revolution around the sun. A tropical year is the time between 2 spring equinoxes, while a sidereal year is about 365.25636 mean solar days. Because Earth is orbiting the sun, it must rotate an additional amount each day to bring the sun back to local solar noon. This takes about 4 minutes, explaining why stars rise earlier each night. If a beam of sunlight is marked at noon every day, it traces out a lopsided figure 8 on the floor over a year. This image shows the path of the sun's direct rays during a year. The sun is high in the northern hemisphere sky during the summer solstice and low during the winter solstice. The shape of Earth's orbit is one factor that causes a difference between sundial time and clock time throughout the year. The angle between the plane of the ecliptic and the plane of the equator is another reason for the difference between sundial time and clock time during the year. The equation of time graph shows how many minutes sundial time is faster or slower than clock time during different months of the year. The standard time zones are shown here. Hawaii and most of Alaska are 2 hours earlier than Pacific Standard Time. The international date line largely follows the 180-degree meridian, but is adjusted so that land areas and island chains maintain the same date.